Section 6.2, Angle and Orthogonality in Inner Product Spaces. We'll start with the Cauchy-Schwarz inequality. If u and v are vectors in a real inner product space V, then the absolute value of the inner product of u and v is less than or equal to the product of the lengths of u and v. Let's prove this real quick. In the case where u equals the zero vector, the two sides of the inequality are equal since the inner product and the length of u will both be zero. So we only need to consider the case where u is not equal to zero. So how about we let a equal the inner product between u and u, b equal 2 times the inner product between u and v, and c equal the inner product between v and v, and we'll let t be any real number. Since the positivity axiom states the inner product of any vector with itself has to be non-negative, it follows that the inner product between tu plus v and tu plus v must be non-negative. It has to be greater than or equal to 0. But we can rewrite the inner product of tu plus v and tu plus v using our properties of the inner product to pull out the t. When we pull out this t, we get 1 in front, and then we pull out this t, we get another, so we end up with t squared. And then we can separate out the u plus v in the first by writing t squared u inner product with u plus v, but then we can separate out the plus v in the second one, so we'll end up with a plus inner product v with v. We'll end up with 2 times the inner product of uv with t and the uu with the t squared. But our shorthand notation that we used, where a was equal to this, b was equal to this, and c was equal to this, now come in handy, and they let us replace this by a, this by b, and this by c. So we end up with a quadratic polynomial in t. So our inequality implies that the quadratic polynomial, at squared plus bt plus c, has either no real roots or a repeated real root because it's greater than or equal to 0. So therefore, its discriminant must satisfy the inequality b squared minus 4ac is less than or equal to 0. Expressing the coefficients a, b, and c in terms of the vectors u and v gives us, well, we're replacing b now. What we said b was 2 inner product u v. So instead of b squared minus 4ac, we'll replace it, and we'll get 4 uv squared instead of b squared minus 4 inner product u with u and v with v. So if b squared minus 4ac is negative, this thing has to be or less than or equal to 0, just non-positive. Or equivalently, the inner product of uv squared has to be less than or equal to the inner product of u with u and v with v. What we'll do is basically just move this to the other side and divide by 4. So taking square roots of both sides, we get the square root of this, square root of this, and using the fact that inner product of u with u and v with v are non-negative, gives us this. But that is literally what we wanted to prove. Perfect, so now we have Cauchy-Schwarz. If u and v are vectors in a real inner product space V, then the angle theta between u and v is defined to be the inverse cosine of the inner product of u and v over their lengths. Very similar to what we saw before with the dot product definition for the angle. Now we just have extended it to the more general real inner product space V. As an example, how about we let M22 have the standard inner product, and we'll find the cosine of the angle between the vectors u and v given. So you might remember that we have the standard inner product from the example 6 of the previous section. So that was 6.1, example 6. That tells us that the inner product between u and v will be 16. All we do is multiply the corresponding components and add them up, corresponding entries. So then if I want the length of u, using that same inner product, it's the square root of 30, just the square root of the inner product of u with itself. So basically just square each entry, add it up, take the square root, and then we'll get to the same thing. We get that the length of v would have to be square root of 14. So that means that the cosine of the angle theta between these two vectors is the inner product of u with v divided by the magnitude of u times the magnitude of v, which is, as we said, 16 over the square root of 30 times the square root of 14. So that's approximately 0.78. If u, v, and w are vectors in a real inner product space v, and if k is a scalar, then the length of u plus v has to be less than or equal to the length of u plus the length of v, and the same thing for the distance, if you want to go to a third vector, w. Two vectors u and v in an inner product space v are called orthogonal if the inner product is 0. Very similar to how we had orthogonality with the dot product being 0. So how about we check if the vectors u and v in example 2 are orthogonal with respect to the Euclidean inner product in R2, and how about with respect to the weighted Euclidean inner product that is given. So what we'll do is we'll compute the dot product, because that's the Euclidean inner product. So the dot product of u and v is 1 times 1 plus 1 times minus 1, which is 0. So that implies that these vectors are orthogonal with respect to the Euclidean inner product. And how about the weighted Euclidean inner product? Let's take that now. Well, using the formula they gave us, that'll be 3 times 1 times 1 plus 2 times 1 times minus 1, which is 1, which is not equal to 0. So that implies that these vectors are not orthogonal with respect to the weighted Euclidean inner product that was given here. So orthogonality depends very heavily on the inner product that is given or chosen. If M22 has the inner product in example 6 of the previous section, then are the matrices U and this one right over here orthogonal? How about I set this one equal to V? So then we have UV, the inner product, using the standard inner product for matrices. We have 1 times 0 plus 0 times 2 plus 1 times 0 plus 1 times 0, by just multiplying the corresponding entries, and that equals 0. So that implies, yes, they are orthogonal. How about we let P2 have the inner product given over here with the integral from -1 to 1 of P of x times Q of x, where P is equal to x, Q is x squared. Let's find the length of P, the length of Q, and show that P and Q are orthogonal relative to the inner product that we're given. So first, let's get the length of P. So the length of P is the square root of the inner product. So I'll write PQ and raise it to the half power. Oh, wait, that's P with P, right? The inner product with itself. Okay, and that is equal to the integral from -1 to 1. P is x, so it's x times x dx. and we'll raise that to the half power. So that's the integral from -1 to 1 of x squared dx raised to the half power, which is the square root of 2/3. Right, you get x cubed over 3, plug in 1, so we get 1/3 minus -1/3, 2/3. Let's do q now. So again, we'll take q with itself. Oops, I wrote p this time. Need q. And raise that to the half. So that's the integral from -1 to 1 of x squared times x squared dx. Raise that to the half. And that is equal to the integral from -1 to 1 of x to the 4th dx. We'll raise that to the half, and we get 2/5. Because get x to the 5th over 5, and then subtract negative x to the 5th over 5, and then we're -1 plugged in. We plug in 1, and then so 1/5 minus -1/5. In any case, take the square root, get square root of 2/5. Lastly, let's get the inner product of p with q. So that's equal to the integral from -1 to 1 of x times x squared dx. And that equals the integral from -1 to 1 of x cubed dx. But if I take x cubed and integrate that from -1 to 1, notice these were even functions, so you could just go to 0 to 1 and double it. X cubed is an odd function over a symmetric interval. We know it's going to be 0. You could double check when you integrate this, take the antiderivative, you get x to the 4th over 4th, plug in 1, plug in -1, it'll end up canceling. In any case, you could see this is 0. So they are orthogonal. Next up, we have the generalized theorem of Pythagoras. If u and v are orthogonal vectors in a real inner product space, then the length of u plus v squared is equal to the length of u squared plus the length of v squared. We could prove this really quick, since the orthogonality of u and v implies that their inner product is 0. So that means that when we rewrite the length of u plus v squared as the inner product of u plus v with u plus v, and then we can expand that outwards, as we've done previously. First you can do a u plus v inner product with u, and add that to u plus v inner product with v, and then split off the u plus v in the first component. In any case, you'll get inner product with u squared plus 2 inner product u with v plus inner product of v with v, and the orthogonality makes this term 0, so it gets eliminated, and we just have length of u squared plus length of v squared. How about we verify this theorem for the vectors p and q and inner product discussed in the previous example. So let's look at the length of p plus q squared. So that'll be the square root of 2/3 squared plus the square root of 2/5 squared, which would be 2/3 plus 2/5, which is 16 over 15 by the theorem. Now let's check it manually and make sure it matches. So length of p plus q, if we compute directly using the inner product, would just be p plus q inner product with p plus q. So that's the integral from -1 to 1 of x plus x squared times x plus x squared dx, which is the integral from -1 to 1 of x squared dx plus 2 times the integral from minus 1 to 1 x cubed dx plus integral from minus 1 to 1 of x to the 4th dx, just by FOILing this out and then applying the linearity of the integral to separate each of the terms into its own integral. And then performing each integral, we get 2/3 plus 0 plus 2/5, which is 16/15. So it matches up. The theorem is a nice little shorthand way of computing this. If W is a subspace of a real inner product space V, then the set of all vectors in V that are orthogonal to every vector in W is called the orthogonal complement of W and is denoted by the symbol W perp. If W is a subspace of a real inner product space V, then A, W perp is also a subspace of V, and B, W intersect W perp is the set of the zero vector. To prove this, let's look at part A first. We have the set W perp contains at least the zero vector, since the inner product of 0 with W would equal 0 for every vector W in W. Thus, it remains to show that W perp is closed under addition and scalar multiplication in order to show it's a subspace. So to do this, let's suppose that U and V are vectors in W perp, so that for every vector W in W, we have the inner product of U and W equal to 0, and the inner product of VW equal to 0. It follows from the additivity and homogeneity axioms of inner products that U plus VW is UW plus VW, but that's 0 plus 0, so it's 0. So that means that it's closed under addition. Similar for scalar multiplication, you can just pull out the scalar. So you get k times 0 is 0, so that inner product is also equal to 0, so that means that both of those vectors are in W perp. It's closed under addition scalar multiplication, it must be a subspace. Let's look at part B now. If V is any vector in both W and W perp, then V is orthogonal to itself. That is, the inner product of V with itself is 0. It follows from the positivity axiom for inner products that V must be equal to 0, because if the inner product is 0, the vector must be 0 by that positivity axiom. If W is a subspace of a real finite dimensional inner product space V, then the orthogonal complement of W perp is W. Not super surprising, the perp kind of cancels out. So we have W perp equals W. Let's let W be the subspace of R6 spanned by the vectors W1 through W4 and find a basis for the orthogonal complement of W. So what I'm going to do is I'm going to write out matrix A that's equal to these W's as rows in the matrix. So my first row will be W1. It'll be 1, 3, minus 2, 0, 2, 0. My second row will be 2, 6, minus 5, minus 2, 4, minus 3 for W2. Then for W3, I have 0, 0, 5, 10, 0, 15. And for W4, I have 2, 6, 0, 8, 4, 18. In section 4.8, example 4, we managed to find a basis for the null space. So it's example 4.8.4, example 4 in section 4.8. That gave us vectors v1 equal to minus 3, 1, 0, 0, 0, 0, v2 equal to minus 4, 0, minus 2, 1, 0, 0, and v3 equal to minus 2, 0, 0, 0, 1, 0. So these guys form a basis for the null space of A. Convenient that we have the same matrix as last time, so we don't have to find these again. Okay, so that means that I can write V1 equal to minus 3, 1, 0, 0, 0, 0. V2 equal to minus 4, 0, minus 2, 1, 0, 0. V3 equal to minus 2, 0, 0, 0, 1, 0 as a basis for the orthogonal complement of W.